Hello. Welcome to From Experimentation to Production, Building Enterprise Scalable GeoAI Systems. I'm Daniel Wilson in Esri Professional Services. Today I'm joined by Rob Fletcher, also in Professional Services. So today we're going to talk about a problem that lies in a lot of machine learning teams. That is, you built some system and it works really well running in your Jupyter notebooks, or perhaps it's been deployed elsewhere. But when you're trying to scale this up, you're running into challenges. Today we're going to talk about overcoming some of those burdens and how ArcGIS will help with that. So first off, what is this presentation? Well, it's a discussion of best practices for developing geospatial machine learning. For now, we're going to focus on deep learning for computer vision tasks, but the same principles apply to other models. So what isn't this presentation? Well, this is not a deep dive on the specifics of the software and tools. This is more of a survey of some of the approaches, techniques, and recommendations that the Esri GeoAI team has applied to real-world problems. We're also not going to talk about specific applications. This is not going to be an example of specific deep learning models that we've built, how to train them, or anything like that. What we're talking about here is how do you take a model that you've already trained and turn it into something that your users can take advantage of. If that sounds boring, that's okay. There are plenty of other sessions. Please check out the other videos on the sessions listed here. The times and locations won't be the same, but you should be able to find them on the same listing on YouTube. So machine learning, it's not always easy. In fact, I would say learning machine learning is quite hard. It took me a while to get to where I am, and I'm still learning every day that I do this job. Applying machine learning is also hard. This should come as no surprise because it's taken until the current time that we're in for machine learning to start to be really applicable to real-world problems. Machine learning has been used for decades, but it's really challenging to apply to real-world problems, and we're starting to see an increase in that, mostly due to available tooling and best practices being shared. Deploying machine learning is easy. No, just kidding. Deploying machine learning actually turns out to be one of the biggest challenges in a data science project. First, you have to learn machine learning, and then you have to apply it. And that usually involves tools such as Jupyter notebooks or other tools that you may find useful when applying machine learning. But deploying machine learning, you really can't just take what you put into a Jupyter notebook and expect it to work well in production. Well, you can, and that really depends on the scale you're at. So what we're going to do is try to make this as easy as possible by breaking this down into a few different levels. So why is deploying machine learning so challenging? Well, there's several different types of gaps that we're going to discuss here. First is the development gap. Basically, data scientists typically aren't good programmers. They're not, we shouldn't expect them to be. Software engineers typically aren't good at machine learning. The two can work together to produce machine learning models, and there's been new roles that have been created to try to bridge this gap in terms of skill sets, but oftentimes you're left as a data scientist trying to deploy to production because people are expecting you to, or you're a software engineer and you don't know as much about machine learning. Someone handed you a model and you're like, well, what do I do with this? Well, machine learning models aren't really any different, but there's a lot of differences in the way that they're applied. Second, machine learning is mostly Python. Most production software isn't. There are, of course, exceptions to this, but most developers are more comfortable working in a more robust programming language, such as one that is strongly typed. And Machine learning is likely to be in Python, for the most part, for the near future. We're going to talk about some tricks that allow data scientists to work in Python and software developers to apply these machine learning models in a language that they are more comfortable in or that their production software is written in. The next gap is the data gap. So basically, this data set was great for my model, but now what? Third, reproducibility. We've all heard this before. It worked on my machine. Why isn't it working now? Machine learning comes with its own unique set of challenges, and we'll discuss some of those. Lastly, is the scale gap. How do I take my experiment to many users? You run a machine learning model in a Jupyter notebook, you produce some results, that gets you some great feedback. Leadership is all excited, and now you want to scale it. How do you do that? We're going to discuss these 4 gaps and how ArcGIS helps with this. So how does ArcGIS help? Well, first, the development gap. Well, in the ArcGIS ecosystem, Python is a first-class citizen. So while ArcGIS is not implemented in pure Python, a machine learning model that is can be easily deployed as a geoprocessing tool or another set of capabilities within the ArcGIS platform. ArcGIS also provides utilities to help productionize these tools, like the ability to create geoprocessing tools and deploy them to server. You don't have to worry about the server infrastructure or scaling it. You just have to worry about making your tool work for the job that you want. Next is the data gap. ArcGIS data stores and services make data management simple. You can store data that is in many formats, including raster and vector data in relational databases. And then geoprocessing tools help standardize your data pipelines. So instead of writing all of this from scratch and making sure it works, you can apply straightforward geoprocessing tools to help manage your data. Third, reproducibility. Well, ArcGIS Notebooks, as I mentioned, is not really for deploying a production machine learning model, but ArcGIS Notebooks is really important in the development process. Now, if you've developed something on a Jupyter notebook that is within ArcGIS Notebooks, you can share that with your teammates and don't have to worry about reproducing the environment because it's already going to be running in the same environment. ArcGIS Notebooks runs in Docker, so you can create custom runtimes to have special situations handled. So for example, if you need some certain libraries or utilities in order for your Jupyter Notebooks to run, you can install that runtime and share that with your teammates. Now, instead of giving them an IPython notebook, an environment file, and who knows how many other dependencies, a poorly written help file, instead you can just point them to your notebook, share the item on portal, and you're good to go. Next, standard data services, such as those available through the Living Atlas, ensure model reproducibility. So if you train a model on, for example, the National Agriculture Imagery Program, I think I said that right, NAPE. If you wanted to use NAPE as your image service that you're applying, you could just point someone to the imagery layer, and they'll have the same exact data that you use without having to share gigabytes or terabytes or petabytes of imagery data. Finally, the scale gap. So ArcGIS can auto-scale services as needed within the required within the required ranges. So that's of course within fixed hardware constraints. You have your deployment of ArcGIS server. You can scale up geoprocessing services or any other tools that you need, and those will scale with demand. So if many users are using the system, that will scale up within your system. And if they're not using it, those resources you can set them to spin down and don't have to use as much. Lastly, you can integrate with elastic scaling. So that's when the hardware scales on demand. So you might not have a fixed deployment. Maybe you want hundreds of GPUs for a moment, and that's when we turn to technologies like Kubernetes that Rob will discuss a little bit later. So the key technologies we're going to talk about today are ArcGIS Pro, Raster Analytics Server, Onix, the Open Neural Network Exchange format, Kubernetes, and then we're going to briefly talk about machine learning services, Azure, AWS, or insert your favorite public cloud here. We're going to focus on the Azure Machine Learning Service. All right, so let's break this into a few different scenarios. Scenario 1. I need a deep learning model to extract building footprints. It needs to be run infrequently for a few areas in my city. So let's pause for a second. This scenario is really talking about someone who works in a small municipality. They want to add value to their workflows by integrating a deep learning model. In this case, what they want to be able to do is update building footprints. Maybe there's construction that's occurring, and these change every now and then, but they want to be able to update the building footprints infrequently, let's say once a year or every few months. Well, in this case, the primary technologies that we would recommend you using are ArcGIS Pro and then a deep learning framework of choice. Using your framework of choice, you can train a model and run that in ArcGIS Pro and share the results with Enterprise, ArcGIS Online, or any local systems that you have. So really, if you're using this paradigm, train your model, you're nearly there. Basically, it's business as usual, as you're used to with ArcGIS. Use Model Builder, or you create custom Python toolboxes or script tools if you need more advanced functionality. And then you can use the ArcGIS API for Python. This allows you to train models with very, very little code. For examples of this, see the public GitHub documentation for the ArcGIS API for Python. There are many example notebooks on how to train deep learning models there. But once you have those, they're already prepackaged and ready to run on ArcGIS Pro after you've installed the deep learning framework. In this case, ArcGIS Learn relies on FastAI and PyTorch in order to achieve its simplicity. Scenario 2. This is very similar, but we're going to start highlighting differences as we scale up these scenarios. So scenario 2. I need a deep learning model to extract building footprints, but it needs to be run on demand by my teammates. So really, we're talking about a deep learning model that you've created, but you're not always going to be the one that's running it. So this is getting closer to what most people would call a production situation. And all of these are production. Really, the point here is that you can use ArcGIS to run things in production. Use that as your production system. You don't have to build everything from scratch. But in the case of scenario 2, we're now talking about expanding out to more people using the tools that you've created. In this case, we're talking about ArcGIS Pro plus the image/spatial analyst extension, ArcGIS Enterprise, and then again a deep learning framework of your choice. In this case, ArcGIS Enterprise fulfills the role of potentially running a machine learning model if it's not a deep learning model, or providing the portal for which you can share your model. So the model could be published as a geoprocessing service, or if you're talking about a deep learning model, you can upload a deep learning package to Portal. Your teammates can download this model and run it using ArcGIS Pro if that's the workflow that they're used to. We will talk about the enterprise version of running deep learning models a little bit later. That is called Raster Analytics. So really what you do here is you package up your model so that you can share it on Portal. This is a screenshot of some of the deep learning models that we have on our portal. In this case, you see house damage classifier, a feature classification model, building footprint unit, road damage unit, and XU baseline. XU baseline was actually a model that we downloaded. It was a publicly available model, and we wrapped it up so that we could run it in ArcGIS. This is exactly what you would expect to do. A deep learning package is all of the files required to run your model. So for most deep learning frameworks, you're going to export a weight file. running your model against a image, usually represented as a NumPy array, is usually pretty simple. However, how do you get that to run in ArcGIS? Well, there's a series of deep learning tools that will be talked about in the other machine learning related workshops and presentations that you should check out if you're interested. But basically, there are 4 components, or potentially less. An EMD, an Esri model definition file. Basically, it contains metadata describing what your model needs to run. The model's weights, if any, we'll go into that later. A custom raster function, not a customer raster function, but a custom raster function. That might be needed if the deep learning model that you have run is not currently supported out of the box. Currently, we support the TensorFlow Object Detection API, ArcGIS Learn, and a few others. The last thing that it could have is additional code or libraries needed to run your model. If you have something really custom, all you have to do is package up all that extra code with the deep learning model, and then you can package everything together in one object that anyone can use. In this case, your teammates will need ArcGIS Pro configured with the deep learning framework or any other custom libraries that are not included in your deep learning package, but then they should be able to run the model with no problem. These models not only can be used with ArcGIS Pro, but you can also use them in Raster Analytics Server, which we'll discuss. Let's look at a little bit more detail on this EMD file, because I kind of just talked about what it looks like at a high level. So in this case, we're looking at an EMD file for a lane cover classification model. In this case, you notice at the top it says that the framework is TensorFlow. That specifies that it will be using a TensorFlow-related raster function. This is referencing a local path here, but you actually don't have to specify that directly. You can specify the inference function. In this case, we're using the TensorFlow Deep Lab implementation. The model file, so this is the weights file that's included in the DLPK. Right here it has frozen inference graph.pb, or protobuffer. The model type in this case is image classification. So that is going to classify each pixel as one of the classes listed below. Extract band 0, 1, 2 tells us that we're running this on these bands, red, green, and blue, and that it's going to be run on an image height and width of 513 by 513 in this case. And then this is a list of the classes and the colors that we want the classifier to assign. When we run this model, this will create a new imagery layer or image data set, and each pixel will be assigned one of these colors and this name. You can obviously specify a lot more. This is not meant to be a full overview of an Esri model definition file, just a quick introduction. Scenario 3. I need a deep learning model to extract building footprints, again, but I need to run it over a large area fairly often. So this might be something where I'm running it every few days, once a week. Depends on the area. Again, these scenarios are a little bit fuzzy. Depending on what exactly you need, you may have to overlap between these. In this case, what we recommend is ArcGIS Pro, mostly for the data preparation pipeline and publishing your model, interacting with ArcGIS Enterprise. And then ArcGIS Enterprise with Image Server to host imagery layers and results of deep learning models. And then Raster Analytics to run deep learning models or other raster processing that's required. And then, of course, a framework of your choice. A deployment of Raster Analytics for geospatial deep learning looks something like this. This is not exactly what it will look like for every specific deployment, but imagine you have Portal. So this is your gateway to get to your models or any results. From there, you can interact with it with ArcGIS Pro. You can look at web maps, web applications. For example, you can run deep learning models directly from Web App Builder. It's actually not as commonly known as I thought it was, but it's very powerful. You can just create a web map and run a deep learning model directly from there using Raster Analytics. We'll go into that in a second. And then you can host everything, wherever. This could be local hardware, or in this case, we're referencing a cloud deployment. In this case, the cloud deployment means that we can put our imagery data store on a cloud data set. For example, Amazon S3, Azure Blob Storage, or you could even use a HDFS. So this gives us a distributed raster store. This could be source imagery that we're going to run a deep learning model against, but it also contains imagery layers that are results of a deep learning model, such as a semantic segmentation model. It's worth pausing on this cloud data store for just a second. So we're talking about a distributed raster store, and why is that important? Well, if we're running these models at scale, we could be talking about massive amounts of data. It could be gigabytes, terabytes, or even petabytes of data. And managing this storage locally could be expensive, and it can also be very difficult to manage a lot of different connections from local storage. There are obviously solutions there, but on a lot of our large-scale deployments, we tend to look at cloud deployments, store our imagery in S3 or Azure Blob. We've actually done deployments with both and seen very, very good performance. But in addition to that, you also are able to scale up as needed. So rather than buying hardware and storing the amount of imagery you have today, you can scale up your deployment without changing the underlying server. Just point to your same S3 bucket or Azure Blob, and you're good to go. We also have image server for raster analytics. So that's a server role designed for raster analytics, and then image server for hosting and basic processing. So basically serving your image services. We also recommend interacting with all of this through Notebook Server. That way everything's in one environment. So if you're using Jupyter Notebooks, you can share those with your teammates. You can publish models directly from a Jupyter Notebook, or create it and then download it for local use in ArcGIS Pro. It's really up to you, but this is what the general platform looks like. So scenario 4. I need a deep learning model to extract building footprints, but I need to run it over a large area fairly often, and I need to do it fast. Well, in this case, we're talking about the same thing, basically, but you'll notice one difference. We're using ArcGIS Pro, we're using ArcGIS Enterprise, Image Server, and Raster Analytics, but in addition to that, we're also going to use the Onix runtime. So what is Onix? So basically, there's all these deep learning frameworks. The ones that you're probably most familiar with are TensorFlow and Keras, PyTorch. My personal favorite is PyTorch, but there's also many others, including ones that aren't listed here. Many of them support what's called the Open Neural Network Exchange format. Basically, Onix is a way of exporting your model. So all of the computation graphs, all of the weights, and everything that your model needs to run, as long as it's a supported Onix operation, into a single file. Now, the idea of that file is that I can take it and share it with anyone else. And all they need to run it is the Onix runtime. They don't need all of the dependencies of PyTorch or TensorFlow or Keras or anything else that I've used to train the model. Instead, they just need the Onix runtime and its dependencies, as long as they have a version that supports the operations that you have. Basically, make sure you're keeping track of the version of Onix you're using to support it. Make sure that your operations set or opset is the correct version, and then this can be deployed. Now, in addition to being training framework agnostic, Onix is also deployment target agnostic. Well, not quite agnostic, but it can support a lot of different devices. So not only can an Onix model be run on CPU with greater performance, it can be run on a GPU, an FPGA, or field programmable gate array, or NPU, which I believe is a neuromorphic processing unit, or something like that. I haven't used them personally. Now, this might not seem important right now because installing a deep learning framework isn't that challenging. But some of these deployments targets can actually involve even more complex runtimes. So what we haven't discussed but you can actually speed up models significantly using Onix. So it's not just a convenient format, but you'll actually get a lot better runtime performance usually with Onix, just plain and simple, because it's optimized, it doesn't have any additional fluff, it's not relying on any one framework. Everything can be optimized when you export it. But also, you can use other runtimes on top of Onix, such as TensorRT, which is an NVIDIA-specific runtime that that can perform additional other optimizations and get really, really high speed. So things like TensorRT allow you to get even better performance. You can go down the rabbit hole of optimizing your model to death, and that's kind of what we're talking about here, is using Onix to scale up your raster analytics deployment. So if you have the Onix runtime installed on every raster analytics server, you're going to be gaining speed and saving time and money by using this. We're not saying you shouldn't use this for a small deployment, but if you have a really small deployment, it might just be worthwhile to use whatever training framework you're working with. But in general, the best practices that we recommend are to use the Onix run. Now I'm going to turn it over to Rob Fletcher, who's going to discuss larger scale deployments.
Thank you, Daniel. So now you want to scale up even more. You want to run a model on a very large area, you want to do it often, and you need the results as quickly as possible. To accomplish this, we can bring in another tool called Kubernetes. For those of you who aren't familiar with it, Kubernetes is a system to automate the deployment, the scaling, and the management of containerized applications. Kubernetes can allow you to scale up to many machines with lots of compute to get results very, very quickly. In order to use Kubernetes, we need to package our model up into a Docker container. Just like before, we recommend using the Onix runtime. This tends to make Docker containers easier to create and maintain, as well as getting all the performance benefits from Onix. In addition, you will need some sort of interface like REST or gRPC. This interface just provides a way for you to send your image data into the model and into the container, and then receive the result. The details of this are up to you, and there are lots of ways that this could be done. Earlier, we saw how an EMD can be used with raster analytics to tell the Esri platform how to run your model. When using an architecture like this, including Kubernetes, we can replace the bits of code that run the model with code that makes calls to your API so that the actual compute takes place in the Kubernetes cluster. We can then take advantage of the scaling capabilities that Kubernetes brings to the table. This allows us to use raster analytics to manage all of our imagery, sending it to the cluster, as well as putting the results from our model back together to then host on your portal as an image or feature service. The downside of using Kubernetes is that it comes with some management overhead and sometimes needs specialized technical resources to set up and administer the cluster. This scenario doesn't necessarily represent scaling up relative to the others. It's more of a wild card that doesn't really fit in anywhere else. In some cases, you may have reasons to keep your machine learning and your GIS platforms completely separate. So in scenario 6, I don't want to manage or host my infrastructure, and I want to keep my GIS out of my machine learning. This might be because machine learning portion of your project doesn't actually use GIS data. Maybe it's text or audio, and you need to run your models on these before you can bring them into the results into the GIS platform. The major cloud providers now have machine learning environments that you can use. For instance, AWS SageMaker and Azure Machine Learning. These systems allow you to manage the lifecycle of both datasets and machine learning models. In Azure Machine Learning, for example, you can register a dataset, train on it, then deploy the model that results from this to either a container instance or to the Azure Kubernetes service. This model can then be called from the ArcGIS platform if needed. These are great services that provide a lot of features, but they can be really difficult to deal with geospatial data. Scenario 7, this still isn't enough. You're in a minority of users. Custom integrations are possible, and we have done some. But if you fall into this category, I recommend that you Stay tuned and look for the talk called The Road Ahead, ArcGIS Enterprise, that should be appearing somewhere soon. Also, let us know what you're actually doing. I'd be really curious to hear about it. Please let us know if you have any questions or comments. We'd love to hear from you. Thanks.